Hello everyone, my name is Sahil, and today I'll be talking about some improved truthful mechanisms for combinatorial auctions, in particular for subadditive bidders. And this is joint work with Seppo Assadi, who's a faculty at Rutgers University, and Thomas Kesselheim, who's a faculty at University of Bonn. So let's start off with the basic setup. So in combinatorial auctions, the main idea is that you have m items, and which you want to distribute between n bidders. So in particular, these items are indivisible and not identical. They're not identical. So you need to come up with a partition or an allocation of these items to these bidders so as to maximize the happiness of these bidders. So what do I mean by happiness? Basically, there's some valuation function. So for a subset of items that a bidder receives, they have some happiness. This is also known as their valuation function or their welfare. So the goal is you want to come up with some allocations of these items so as to maximize the total happiness or the total welfare. So summation over I via SI, where SI is the set of items that get allocated to bidder I. So the difficulty comes because of multiple reasons. One is, okay, you need to do it in polynomial time. The other challenge comes because these valuation functions will be private. I mean, there's going to be a personal information of this bidder, and I'll get to it in a bit. But that's the high level problem. And now we're interested in many kinds of valuation functions. In particular, the simplest one are the additive functions, where if I give you two items, your valuation for the set of two items is just the sum of the values of both items. But we are also interested, I mean, the main focus of today's talk is actually about subadditive functions, which are not necessarily additive. In fact, as you get more and more items, the marginal values kind of decrease. So it's a much general class than submodular or XOR functions. Okay, so this was the informal setup, and now let me get a little bit formal. So first of all, let's look at even what's the purely algorithmic question. What do we know there? So in a purely algorithmic question, I mean, like, suppose I even give you these valuation functions, all of these bidders. I suppose you know their valuation, which means like their set functions. You want to come up with a polynomial time algorithm to find these allocations so as to maximize the welfare. If the valuations are additive, then I claim this is a very trivial problem because you can just allocate each item to the bidder who likes it the most. And that's going to just maximize the welfare simply because, I mean, different items are not really interacting with each other. However, if you go beyond additive valuations, you might even wonder how are the valuation functions even given to you? I mean, you need a polynomial size description to it somehow, and that's not possible because for submodular or subadditive functions, it's a set function. And there are 2 to the m possible subsets, which is already exponential in the number of items. So the way we go about this is using an oracle access. So 2 of the most popular oracles are the value oracle and the demand oracle. In a value oracle, you basically have an access to an oracle whom you can query that, okay, for this particular bidder and this particular set of items, what's their value? So you can query VI of S, where VI is the valuation of the ith bidder, and S is some set of items you can query. And an interesting result shows that you can solve this problem approximately using just the value oracle if your valuation functions are submodular. So in particular, even the greedy algorithm gives you 2 approximation. And okay, using like some more work, you can improve this approximation factors slightly to E over E minus 1. However, you cannot, even in polynomial time, you cannot get the optimal allocation, but even for submodular bidders. Interestingly, if you go beyond submodular valuations, in particular to XOS and subadditive. So the main focus of today's talk is actually subadditive. There, it's known that, okay, value oracle does not suffice. In general, like for using polynomial number of queries to this value oracle, for subadditive bidders, you cannot come up with a constant approximation. However, there is a stronger oracle, it's the so-called known as the demand oracle, which generalizes the value oracle. And I'll define it a bit later in the talk. But using this stronger oracle, you can actually get a constant approximation even for subadditive or XOS bidders. So in particular, I mean, the main takeaway is that for the purely algorithmic problem, if you know the valuation functions up front, then we know constant approximation algorithms, and pretty much we even know the tight approximation factors. And okay, so the focus now is like, how can we handle strategic bidders? So these are basically the bidders when they don't know where the valuations are not known to your algorithm upfront. So formally, what happens, you have n bidders. Each of them is strategic in the sense that they know their own valuation function, but they are trying to be clever about revealing their valuation function to you as in you, the algorithm. So you have m, again, m indivisible items. And You want to allocate them between these and strategic bidders who have some private valuations, which means that you don't know these valuation functions. So, okay, but what do I allow your algorithm? So what your algorithm has to do is to come up with, the formal term is a mechanism. You want to come up with a truthful mechanism. So what does it mean by a truthful mechanism? So this is an algorithm which takes as input the valuation functions of each of these bidders. So you query each of these bidders. Okay, tell me what's your valuation function. Tell me what's your valuation function. Okay, you might worry like the valuation function might again be exponential size. But okay, for a moment, let's not worry about computational constraints. Otherwise, you might want like, okay, can you do even like with using polynomial number amount of communication and so on. But the way the algorithm goes is you first ask each of them like what's their valuation function, and once they reveal their valuation function, you have to come up. Your algorithm has to come up with an allocation and as well as some payments for each of these bidders. Your algorithm's goal is the same. I mean, you want to come up with an allocation which maximizes the welfare. These are the true valuations. However, the bidders need not necessarily report their true valuation function. They might be reporting something else. So you want to come up with a mechanism with an algorithm such that even if when the bidders are trying to maximize the valuation for the set minus this payment, so that's like how much you're charging them to get the set of items. When they're trying to maximize this quantity, they have no incentive to lie. I mean, it's in their best interest to just report truthfully. So they cannot gain by misreporting. And so I won't define it very formally, but that's like how, this is pretty much the definition. And our mechanisms will be very obviously truthful. So I mean, it will be very easy to verify that the mechanisms are very truthful, that the bidders have no incentive to lie. Good. So given all this, now what's an interesting thing is there's a classical result of Vickery, Clark, and Gross, which shows that for any valuation, like even for subadditive valuation functions, there exist algorithms which will get you, which are like, these are truthful mechanisms, which get you the optimal welfare. However, they don't run in polynomial time. So they do run in polynomial time for additive valuations, but as soon as you go beyond, say, submodular valuations and subadditive, then they don't run in polynomial time. So the question becomes, how can we achieve three goals simultaneously? We want to be truthful. We want to be running in polynomial time. So when I say truthful, it means like there should be no incentive to lie. You want your mechanism to run in polynomial time, and it should be approximating the welfare. So it's not that the welfare is like totally off. And the question becomes like, how can we achieve this, all of them simultaneously? And this is kind of like one of the fundamental problems in algorithmic game theory. So what's known about this? Interestingly, for using the value oracle, the simpler of the two oracles, it's known that not much is possible. In general, there's like a polynomial hardness, even for submodular valuations. Notice that using value oracle, if the valuations were given to you, then you could do it in constant approximation, but no more. Like when the bidders are strategic, then it's not possible. However, using the demand oracle, over like in the last 15 years or so, there have been like multiple sequence of results. So started off with some work of Dubzinski, Desan, and Shapira, who got like a log square M approximation, and gradually it has been improved. In particularly in our Fox 2019 paper with Sepper, we got like a polylog log M result. So log M cube for submodular bidders using the demand oracle. And the main underlying open question here is, can we get a constant approximation using the demand oracle for submodular bidders? So although there was like a lot of progress for submodular bidders, for subadditive bidders, this is the more general valuation class, which is a very important class. Here we were still stuck at this 2007 result of Shahar-Dubzinski, where we got like a log M times a log M. And one of the primary reasons was that all these results, like at least till here, or many of the prior techniques, they kind of, at least morally, went by reducing subadditive functions to XOS functions, and then for XOS functions, applying this submodular machinery. So this machinery, actually, all of these results also extend to XOS valuations. So, but the annoyance is that this transformation of a subadditive function to XOS or a XOS function, that loses already a log M factor. So somehow there was like a bottleneck of going beyond log M for subadditive bidders, and that's why we were stuck here. So our main result in this work is that for subadditive bidders, we can get in polynomial time a truthful mechanism, which gets also like a log M cube approximation. So we basically exponentially improved this result of Shahar-Dubzinski from log M to log M cube. As a remark, like we also slightly improved like this work of for submodular bidders where we get like we shave off like one of the log-m's, we bring down the cube to square. But our main contribution in some sense is more for the subadditive bidders because the prior techniques didn't extend there. Okay, so what's the outline for the talk? I just told you what are these truthful combinatorial options. Now I'll be telling you what are these posted price mechanisms. So which is like the main underlying machinery tool that we'll be using. And then like how we use this tool to build our binary search mechanism. So it's going to be some kind of a binary search. Okay, so let's first start off with some prelims. So what's a fixed price auction? A fixed price auction is as follows. You set the price for each item. So it's similar to kind of going to a grocery store. Each item has a price associated with it. And now whenever a bidder walks into the grocery store, they can pick any subset of the remaining items. So any of the items which are not already sold, you can buy any set of them by paying the sum of the prices. So what does the bidder do? If you walk into a grocery store, you basically look at the set S, any subset S of the remaining items to maximize your valuation minus the sum of the prices that you pay. So this is also known as the utility of the bidder. So you're trying to just maximize this. So that's what the bidder do. So what's a fixed price auction? You just set up fixed prices for these items, and now bidders come and walk in one by one. They just take this any set of items, like their best set of items, and then the next bidder comes, and among the remaining items, they take their best set and so on. And the question is like, what approximation of the welfare can we get using these fixed price auctions? And the interesting point about these fixed price auctions is, first of all, they are truthful simply because the prices are fixed. I mean, there's no point in the bidder misreporting or trying to be clever. I mean, all they have to do is just run this query, their best function, and there's no point in being clever about it because they cannot really change the prices. And also, this is polytype simply because the demand oracle, which I hadn't defined on the second slide, it's basically exactly this query. So demand oracle allows us using a single query to answer basically this question, that what's the argmax of this. Good. So now why is this interesting? So the reason this is interesting is because, first of all, okay, a simple example is, for example, if you're just selling a single item, and you want to give it the item to the person who values it the most. Notice that if I set the price to be the second highest valuation among all the bidders, maybe plus an epsilon tending to 0, then notice this will already give me the optimal welfare. Simply because only the highest bidder is going to be willing to pay this much price and nobody else. So that's like shows that, okay, if you set up the prices cleverly, then maybe there is some energy in these kinds of auctions, fixed price auctions. And so the question is like, yeah, do prices always exist that give you high welfare? And this is known to be true. So in particular, this is like from prior works that for submodular and XOS functions, it's a folklore lemma that you can even get a 2 approximation. So there are nice prices such that if you set those prices and the bidders are submodular or XOS, then you can get a 2 approximation. And a very recent work of from Fox 2020 of Paul Duting, Thomas Kesselheim, and Brendan Lucier, they showed that even for subadditive valuation functions, there exist prices which get you a log m approximation. And log m is nice for us because notice we are aiming, that's like polylog m is what we are kind of aiming for. However, there's still the biggest challenge is that, okay, how do I find such prices? These prior works, like, I mean, they were assuming that the valuation functions were known to you upfront, or you had like a nice distribution of them given to you. But if you don't have any such access, like how do you find these prices? How do you learn such prices? So the way we go about it, and like, I mean, some of the prior works have also gone about it, is, okay, let's start off with like some simple warm-up exercises. Like first, when I'm just doing a single item welfare maximization, I just have like a single item to allocate. So, okay, offline, you can run the second price auction, but suppose I want to do it in an online model where bidders arrive one by one. Then here's the secretary problem, like the classical stopping time problem, the secretary problem based mechanism, where you just partition all the bidders randomly into 2 halves, N0 and N1. All the bidders that arrive in N0, you just tell them, okay, you won't be getting this item today, but had you been participating, had you been like, how much would you be willing to pay? So intuitively, you can think of it as conducting some kind of a survey, you can say. So ask all these bidders how much you'll be willing. And now whichever is the highest price among all these bidders in N0. set that as the fixed price for all the bidders in N1. So what do? You randomly partition, ignore all the bidders in N0, but ask them their values. Uh, and notice like these bidders in N0, they don't have any incentive to misreport because anyways, they're not getting the item. And then like whatever is the largest price, that's what you set as the threshold for the bidders in N1. And you run basically just a fixed price auction in N1. And I'm calling sometimes this as posted price mechanism instead of fixed price auction because you're kind of changing the price. And the price for bidder, I mean, the price was infinity for bidders in N0, but this P for N1. But yeah, so clearly there's no incentive for anybody to lie. And this gives you a constant approximation simply because with a constant probability, if this event happens, that the second highest bidder arrives in the first half and the highest bidder arrives in N1. And both of these things happen simultaneously, clearly you're going to get a concept like the item goes to the bidder who has the highest value. Okay, so this is just a warm-up exercise, like why for single item mechanism, you can hope to learn the price or like at least a good price. Good. But now how to go about for selling multiple items. Now here's the idea, again, like a warm-up exercise, which gives you roughly like a log m approximation for selling multiple items. So the idea is as follows. Again, you do similar, like just randomly partition the bidders into two halves, N0 and N1. Bidders in N0, again, you don't allocate them any of the items. You just conduct a survey on them and basically ask them queries, run offline algorithms to get an estimate of the value of the optimal welfare. So what I'm saying is like ignore all the bidders in N0, but ask them their valuations, and which gives you an estimate of opt, a constant estimate of opt, a constant factor estimate of opt simply by concentration. There are some simple like minor corner cases which are easy to handle, but let's ignore that. So now the point is that you basically know the value of opt, you still don't know the allocation. However, the interesting thing is you also know that all the prices of the items you can show, they only need to be in this polynomial range between like opt over m to opt. So m is the number of items. So now what you can do is basically just exponentially bucket. So like say powers of 2. And so there are only log m buckets. And now for each item, separately guess what's its price. I mean, you're just guessing. So for each item, with 1 over log m probability, you're guessing it's nearly its correct price. Okay, and so what you do is as follows. You first use the bidders in N0 to find an estimate of opt. Now for each item, separately guess what's its price within this, like one of these buckets, and set that as its final price and run a fixed price auction on the bidders in N1 using these prices, using these guessed prices. And the idea is that, okay, because you're guessing like the prices like some 1 over log m probability, you'll be getting like a log m approximation to your optimal value. And okay, I'm hand waving a bunch of details here. For example, some major challenges here are, okay, besides even like estimating out, these are easy to handle. There are some other challenges, like it's not that the event that's there is each item's price individually is getting guessed with like a 1 over log m probability. However, the probability of getting all the items prices simultaneously correct is exponentially small. So it's not that I'm getting the same price vector with a decent probability. It's just that each item's individual price might be correct, but most likely, like most other items, many of the other items are incorrectly priced. So I mean, and like in the previous slide, all I was arguing was that there exists some good prices, but I mean, different items prices do interact with each other. And yeah, another annoyance is, okay, this is only giving you a log m approximation at best, and you really want to go ahead. You want to get like a log m. So in prior works, like for example, my joint work with Sepper, like the way we were able to go beyond log m for submodular and XOS functions was because of two observations. One is that the prices turn out to be robust. So these prices, I mean, even if you don't get the entire prices, like prices of all the items correct, only a fraction of them correct, still you can show that, okay, the fixed price auctions, I mean, they work very well. Interestingly, I mean, yeah, we don't know of any such result for subadditive functions. So that's one challenge. I mean, by prior techniques didn't extend. And also, like, okay, we were the way we went beyond log m approximation, even for submodular and XOS, was to actually not learn the prices in a single round, but to actually repeat this kind of like in multiple rounds, partition the bidders into not just two pieces, but like multiple rounds, and then gradually try to get a better and better estimate of the prices. But again, like this is again, like at least when we started the project, it was not clear to us how to implement this step for subadditive valuations. Okay, so I mean, the main challenge is, okay, how to handle both of these challenges for subadditive values. And I mean, our building block, as I had mentioned, like is this recent result of Paul Duting, Thomas Kesselheim, and Brendan Lucier from Fox 2020, where they basically show that, okay, there do exist nice prices for even for subadditive bidders. And their main technical lemma is that, okay, there are some prices such that if T is some any set of items which have been already sold, then the utility of this bidder over some distribution, I mean, in particular, I mean, I'm interested actually in the max, but there exists a distribution such that the expected utility with respect to that distribution over all the remaining items. So T is the set of items which have been already sold, and S minus T is kind of what they're getting, plus the revenue that you've already obtained from the sold items is comparable to like the set of items that this bidder gets in the optimal allocation. So SI star is the optimal allocation to this bidder in SI star. I mean, even if this is confusing, the main takeaway is that they obtain some nice prices, which argue that and argue that either this bidder I has a large utility or the items have been already sold, so you obtain like a large revenue. So the sum of the revenue plus the utility, sum of the utility and the revenue is comparable to the total optimal allocation up to this approximation factor alpha, which is like log m for subadditive. However, there's like naively, if you try to apply this lemma, it's not really robust. Robust in the sense of that if you guess only like 1/10 of the items, like you guess correctly their prices, and 90% are incorrect, it's not at all clear that you're getting like a 1/10 approximation of your welfare. Because these items that you don't correctly guess, then you're really losing additive. Like they appear in this revenue and they appear in this P of theta, which is not good for you. Okay, so we have to go beyond this. So now let me give you like the idea of our binary search mechanism and how we handle this go beyond, like quickly, the high level idea. So our main mechanism is just, you're basically doing some kind of a binary search over all these item prices. So for simplicity, I mean, let's just assume that opt is known to you, like the optimal welfare, say M. As I was saying, this can be easily guessed by partitioning the bidders into two halves. And now you can assume also like all item prices are between say 1 to M. So these are some integers, and let's also define some bins. This is just the exponential bucketing kind of a trick that okay, prices between BJ's, just this bucket. Now I want to do a binary search. So remember, there are log m buckets. So these BJ's, there are log m. So I want to do a binary search over these log m things. So in some sense, I need like a log m iterations, rounds. So what my algorithm does, or my mechanism does, is first it starts off by randomly partitioning the bidders into beta plus 1 groups. So these are my n beta plus 1. Beta is log m. And now I'm going to do is run a fixed price auction on each of these rounds, in each of these bidders, basically, one by one. And so these are going to be separate fixed price auctions. And one of them is going to be finally made my final allocation. So a priori, I don't tell, okay, like that maybe bidder's allocation for N2 is going to be final. So that's not clear. I mean, that's not declared. You just run like a bunch of auctions and only one of them is going to be made final, like with probability 1 over beta plus 1. And just because, and like no bidder has any incentive to misreport because each of them is a fixed price auction. So they cannot really affect their prices. So they behave truthfully. And okay, so now how we do this thing is basically, as I was saying, like a binary search. So at the root level, you start off with all the bins. Now what happens is, okay, the root level, you start off with say bidders in N1. You set item prices. Each item, the point is that each item has its own root leaf path, because for each item, if it gets sold, you move it like raise its price in the next round, and if it does not get sold, you lower its price, and so on. So the main point is that using this binary search, we are using these like whatever feedback we are getting, whether the item gets sold or not, as a proxy to update our prices. And our main technical lemma is that okay, that the expected utility plus the revenue that we get gives us roughly again like this poly beta approximation. So beta is roughly like log. And like once we have this technical lemma, I mean, then the main proof goes off easily simply because I can just sum this up over all the bidders. And the idea for the main technical lemma is as follows. I mean, you just condition on all the bidders in all the rounds. So okay, let's look at what's happening to the utility of plus the revenue of items in SI star. So condition on all the rounds in which other bidders except I arrives. And let's look at what happens to the items, any item in SI star. So it's going to take some path. Now the point is that we are only in one of the following three cases. Either the item gets correctly priced till the leaf. So it's actually taking the optimal path. So if the item have been optimally priced here, then that's what really happens. In absence of this, then I mean you're in great shape because there's there's a significant chance that this bidder arrives in the last round, which is like a 1 over beta. Otherwise, the item gets lost. I mean, it doesn't reach the correct leaf. You don't get its correct price, but then you can price it correctly somewhere. But then it was either lost because it was priced higher at some point in the beginning and somebody bought it, but then your revenue becomes large. On the other hand, it's lost because it was priced low and still nobody bought it. But then this bidder could have arrived earlier and bought it. So that's basically like a simple case analysis. And yet, once you combine this thing along with this lemma of DKL, then you basically get the right approximation factor. So I'm just like giving the high level idea. Okay, so to conclude that, okay, what we obtain is a polylog logarithm approximation. And the main idea is to run the secretary problem-based posted price mechanisms and do a binary search. And one of the major open questions is, okay, can we get a constant approximation? And even for submodular bidders, that's totally unclear right now. Thank you.